Okay. Now you should hear.
Sorry, do I need to start from the beginning?
Okay. We have time, so if you like, yes.
Huh?
Here?
No.
No, in the PDF.
The PDF.
Yeah.
Adobe. The first one.
The
On the left.
Oh,
Yes.
yes.
Okay, as you prefer, Serena. If you want to start from the beginning, for me it's okay, just because we had this problem. It's 9 minutes that we can, let's say, get from the rest of the presentation.
Okay.
As you like. If you can start, you can
maybe
start from here, or you can just start from the beginning.
What?
As you like.
Is it a problem if I continue?
You can continue.
So I think the first part is easy to understand.
Yes.
So I will skip the introduction maybe, and I will start from here to save some time. And so, okay, here it's obvious what's happening. So we want to support the archaeologists in doing this work. And the problem is that there are no suitable training data for this task. And synthetic data set, lack of the ground truth we need for the task, and real world data set do not have enough data to train a model. So and the other problem is that there is no available data set with 3D models of pottery that we can use to build another data set for our task. So we decided to create our own, and we started from the beginning. We discussed with the archaeologists, and starting from photo reference from the cultural heritage catalog, we modeled 3D model of Nuragic pottery, and using Blender, which is free-to-use open source software with an active Python API, and we generated then a data set with 5 different classes based on the time period and the presence in the archaeological site. Then we simulated the breakage of this pottery. So for just one single model, we used the add-on of Blender, which is called Self Fractures. So it creates a bounding box around the mesh of our model. It selects a number of seeds which is tunable by the user, and it constructs a 3D Voronoi diagram with these seeds. Then it intersects the object with the Voronoi diagram and obtains the individual fragments. Then for each piece obtaining like that, we retriangulate and remesh in order to have a better distribution of the point, especially alongside the breakage surface. We validate the mesh, meaning we took only those meshes of the piece that have a minimum size of the bounding box and the minimum number of mesh points. And then the meshes of the fragments are exported in STL format and saved with a universally unique identifier code. So at the end of this pipeline, we have our fragments and a ground truth adjacency matrix, which maps each fragment with all the fragments that are neighbors. Then all this process is done with the API of Blender, the Python API of Blender. So no graphical user interface is needed, and it is just a Python script. To break just one mesh, we have a computing time of the order of few tenths of seconds, even less. But if you want to scale up this process to have a large data set, we cannot think about make this pipeline in series. What helps us is that this workload is embarrassingly parallel, meaning each breakage is independent from the other, so we can easily distribute our computing and containerize our pipeline using Obtainer and distribute it, the computing in different nodes. So Obtainer is used to containerize the pipeline of the breakage here. And then we use the SnakeMake to manage the file system and to manage the dispatch of the jobs in the different nodes. And we use Slurm to dispatch the job in different computing nodes. Actually, this is done under the hood using SnakeMake. So after all, after that, SnakeMake retrieves the results from the computing nodes and save them to the file system. And then we obtain different breakage for all the different classes. Okay, so we were satisfied about our job, but we needed to simulate the real world as better as possible. So we decided to simulate also the erosion of time, of the effect of the erosion of time in the fragments. And the idea is that as time passes, the effect of the erosion is stronger on sharp surface, and it's weaker on flat surface. And if we transpose these to mesh points, the idea is that the variation in time of the position of the mesh point is proportional to the mean curvature in that point. So if we consider the mesh points as a set of point with a certain position in the 3D space, and then the curvature as a vector which is the curvature in that point, and the normal vector to the surface in that point, we can model the variation of the position of the mesh point in time. We know that the variation of the position of the point in time is proportional to the curvature. So we can model this variation using this ordinary differential equation, to which we add the curvature strength, this parameter mu, which is tunable, and this other parameter, which is random noise that simulates eventual extra damage during time, and with this sigma, which is also tunable. And we can solve this equation at each time step, and this is how we solve it. How we calculate the variation of the position of the point at each time step. So we can solve this equation iteratively for each point of the point cloud at each time step. And as you can see from the figure here, you can see the results of this erosion simulation at different values of mu. As you can see, as the value is higher, you have you obtain a surface which is highly damaged, and in the sharp part, the sharp surface are smoother and smoother. So at the end of this pipeline, the user who wants to create this dataset has access to a tunable number of random breaks mode, which determines the number of subjobs of the pipeline, and a tunable number of fragments per break, which determines how many seeds in the Voronoi diagrams are. And we, as a group, created a dataset using a random number of breaks. A number of breaks modes of 60, and each break mode has a fragment per break, which goes from 6 to 16. And at the end, we obtain a dataset of more than 3,000 fragments in total, and we eroded them using these parameters. And this dataset is available in open access. at the INFN open access repository here. And here you can see in the slide an example of fragments eroded and for each class. So to conclude the presentation, as I said, the manual reconstruction of broken ceramics is very time consuming and relies heavily on the knowledge of the experts. Deep learning can support the archaeologists in doing this job. However, training datasets are scarce, so we overcome these bottlenecks by creating our own dataset. The dataset is actually by creating a pipeline to create the dataset, which is open source and fully containerized. So the pipeline is ready to distribute, containerized, and it is reproducible and scalable, and has no complex dependency management. The erosion module is implemented in PyTorch, so as it has a simple interface and it is GPU accelerated, and the dataset is freely available to anyone who wants to use it with all the ground truth needed for the tasks. So for the future work, we can use this dataset to train a model for the fragment classification, for orientation and regression of the fragments in the 3D space, and finally we can use the dataset to train a model which for the fragment pairing and reconstruction of the pottery vessels. Thank you.
Thank you, Serena. Any comment from remotely or from the Platea? If not, I have one for you, and is how you plan to, let's say, increase the number of data that you have, a number of fragments. So is that, have you planning a strategy to increment the number of data that can be used for this study, or?
Okay, so as you can see, we only have 5 classes, and we are working to increase the variation in classes. So we will have a data set that for each class has different styles, let's say, of pottery, in order to have a better simulation of the real world, because obviously it's not just those 5 pottery vessels, but they can vary in form and dimensions. And another thing we can do is that if we vary from archaeological site to archaeological site, we can add different classes. I mean, if I go to another archaeological site and here there are different classes of pottery, we can add to the dataset other models and then retrain a pre-trained model, like doing a fine-tuning of the models to the new classes.
Okay, thank you. Okay. Thank you, and also thanks to stay in the time. Thank you again, Serena. Many thanks. And then what we have is the next speaker that from my chart is Berat. Berat, are you here?
Yes, yes, I am here. Can you hear me?
Okay, yes, I can hear you, but with some echo. So, but in any case, just start with to share the presentation.
Okay.
And then we will also tune the microphone if needed.
Can you see right now?
Oh, yes, I can see the already in the full screen. Okay.
Okay,
So,
I'm starting now.
Yes, brother, the floor is yours, please.
Good afternoon and hello everyone. My name is Beratcan Karakash and I'm presenting on behalf of our research team at Yıldız Technical University and the University of Georgia and the Fibobanca R&D Center. Today, I will be talking about our paper titled A Generative and Cluster-Aware Approach to Fraud Detection. Let's get started. Uh, Before diving in, what brought us here? Financial fraud is evolving faster than the tools we use to detect it. This talk is about why existing approaches fall short and what we built to address that. Financial fraud in digital banking remains one of the most costly challenges in the industry, causing billions of dollars in annual losses in the worldwide. When we look at the real world fraud detection,
Wait, I think that we lost the sharing.
okay, I will share again.
Check, please. Okay, now it's here.
Okay. When we look at the real world fraud detection, two simultaneous problems make this especially hard. First one, extreme class imbalance. In our datasets, fraudulent transactions represent only 0.17% of all activities. Second one, behavioral heterogeneity. Fraud is not the one thing. It takes many different forms, and those patterns evolve constantly. The key insight we want to highlight is this: standard approaches fail precisely because they addresses these two problems independently. Smooth-based oversampling creates synthetic samples through linear interpolation, which produces unrealistic data points in high-dimensional multimodal feature spaces. And the monolithic global classifier simply cannot capture the rare localized fraud subpatterns that exist in the data. Our answer is dual-layered, cluster-aware multimodal framework, one that jointly addresses both challenges through generative oversampling with CT-GAN of mixture of experts architecture built on UMAP and the DB scan clustering. Now, let me walk through the three research questions that guided this work. Prior work on fraud detection generally falls into three streams. In supervised approach, like decision trees, pardon. Our study is organized around three core research questions. First, can CT-GAN-based generative oversampling actually outperforms classical methods like Smooth and RAS on real benchmark? We tested these on the well-known European 2013 credit card dataset. Second, does explicitly modeling the heterogeneity of fraud using clustering to identify distinct behavioral subgroups and routing each to specialized expert lead to better detection than a single global model? And the third, can we combine these two ideas into the unified framework that achieve state-of-art F1 performance while remaining operationally viable, meaning high recall under a 19% precision constraint and a measurable cost saving? As we will see, the answer to all three is yes. To understand where we fit in the literature, let me briefly cover related work. Mm, Now, prior work on fraud detection generally falls into three streams. In supervised approach, methods like decision trees, logistic regressions, and the neural networks serve as standard baselines. A key landmark here is the work of Dalpazol and the colleagues from 2015. They showed that accuracy-driven models systematically fail under class imbalance, and they establish a fun score and the cost-sensitive metric as the right way to evaluate fraud detectors. For imbalance learning, smooth became the dominant technique, but as Xu et al. Demonstrated at Near IPS 2019, a linear interpolation in high-dimensional multimodal spaces produces synthetic samples that don't reflect the true data distribution. Their CT-GAN model, which learns this which learns the generative distribution directly, was a significant step forward, and it's the foundation of our first layer. Finally, in the multimodal architectures, the most relevant recent work is Galwash et al. From 2025, who showed that DB-scan augmented ensemble can meaningfully improve detection by exploiting a fraud substructure. Our framework builds directly on that insight, and as we will see, they push it further. Before diving into the methodology, it's worth framing where this work sits from an industrial perspective. This isn't just an academic exercise. The framework is designed to plug directly into real banking infrastructure. The mixture of expert architecture functions as a high capacity API layer at the core banking gateway. Cluster behavioral data feeds into security operations centers for cyber threat correlations. Clustered anomalies supports human-in-the-loop review in case management. And the traceable cluster structure directly supports compliance and AML audits requirements. This real-world grounding is part of what makes the framework operationally meaningful. Now, what's happened? Uh, Now let's get into methodology itself. Our proposed framework is end-to-end three-layer pipeline. Layer one handles data augmentation via CT-GAN. This is where we address this class imbalance by generating high-fidelity synthetic fraud samples. Layer 2 applies UMA for dimensionality reduction, followed by DB scan clustering. This is where we decompose the fraud population into behaviorally distinct subgroups. Layer 3 is the mixture of expert routing architecture. Each transaction is assigned to the cluster-specific expert classifier best suited to detect the type of fraud. Together, these three layers form an integrated system where each component reinforces the others. Uh, Let me now go deeper on layer one, the CT-GAN component. CT-GAN is trained exclusively on fraudulent transaction. CTGAN is trained exclusively on fraudulent transactions. This is critical design choice. It's learned the true nonlinear distribution of fraud rather than interpolating between existing sample as a smooth does. It captures complex multimodal feature dependencies across all dimensionals simultaneously. We generate three synthetic fraud samples per real instance and validate their quality statistically. The distribution alignment scores confirm the synthetic data closely mirrors the real fraud distribution. The bottom line, CTGAN improves mean F1 by nearly 3 percentage points over the ensemble baseline, and the base individual classifiers, XGBoost and LightGBM, reach an F1 in the high 80s. Now for the layer 2, the clustering pipeline. We apply UMAP to project fraud-only training samples into low-dimensional embedding space. The key here is the UMAP preserve the nonlinear topological structure of the data, something PCA alone cannot do, which gives DB scan much cleaner density regions to work with. We then run DB scan on this embedding with the epsilon parameter tuned while the k-distance elbow method to avoid arbitrary choices. To ensure each cluster is statistically meaningful at test time, we apply a dynamic merging steps and the cluster too small to be reliable gets absorbed into its nearest neighbor. This is bootstrap validated. The result, nearly 500 fraudulent transactions decompose into 6 behaviorally consistent microclusters, each representing a distinct and learnable fraud patterns. With the methodology in place, let's look at the experimental results. Our experiments used well-established European cardholders 2013 benchmark, over 200,000 transactions where fraud accounts for less than a fifth of percent of all activities. This extreme imbalance is precisely what makes it a relevant and challenging benchmark. We use a stratified train validation test splits to preserve that class distribution across all sets, and we test five classifiers: random forest, AdaBoost, CatBoost, XGBoost, and the light GBM, each under five different resampling strategy, including our proposed CT-GAN approach. Our primary metric is F1 score, which balances precision and recall. We also report recall at a fixed precision threshold and the cost saving to reflect real-world banking constraints. Here are the CT-GAN oversampling results. The CT-GAN column on the far right is the top performer across all five classifiers, which without exceptions. The gains are consistent and meaningful, not marginal improvement. What's particularly striking is the RAS columns. Random undersampling actually hurts performance relative to doing nothing at all for most models. Smooth and smoothen offer some improvement, but CT-GAN is a different league. This directly answers our first research question. Generative oversampling with CT-GAN clearly outperforms all traditional interpolation-based methods. Now, let's look at the cluster-aware multimodal results. The headline finding is 5 out of 6 clusters achieve an F1 above 0.90, and 3 of those reach a perfect score 1, meaning 0 missed fraud, 0 false alarm for those cluster-specific experts. The one exception is cluster 3, which underperformed significantly. This isn't a flaw in the framework. It reflects a genuinely ambiguous fraud subpattern where the behavioral signal is weaker. It's actually a valuable finding that points us toward future work. Importantly, we verified that the aggregated result has zero overlap between clusters. Every transaction is counted exactly once. The system correctly identifies the vast majority of fraud cases with only a handful of false alarm across the entire test set. This answer is our second research questions, specializing by fraud behavior type rather than using one global model makes a measurable differences. Before I show the numbers, I want to transparent about something. The gains here are incremental, not dramatic, going from F1 0.87 and to 0.90 took significant engineering effort across the full pipeline. But in fraud detection, each percentage point of recall translates directly to real financial loss prevented, and the 85% cost saving versus 74% is a meaningful operational difference in a live banking system. These slides bring everything is together, comparing our mixture of expert system against the global baseline, the same CT-GAN augmentation but a single classifier instead of specialized expert. We see a clear improvement in both F1 and cost saving. The multimodal routing is doing meaningful work on the top of the generative oversampling alone. Now, looking at the broader benchmark landscape, uh, Del Pozo and the college achieved an F1 around 0.81, and Young et al. Federated learning approach improved at a roughly 0.87, and Galwesh et al. Almost direct predecessors reach 0.87 with the DB scan augmented ensemble. Our proposed framework achieve an F1 of 0.80, 90, pardon. A new state of art on this benchmark and a meaningful step beyond the prior best. To make this concentrate, in our test sets of 74 fraud cases, the baseline model misses 90s, 19, while our proposed system misses only 11. 8 additional fraud cases count, using the ECB's 2025 benchmark of approximately 78 euros average loss per fraudulent card transaction. That's roughly €600 in additional prevented loss on test sets alone. And at production scale, this compounds into meaningful reduction in a chargeback and reputational risk, now not just raw financial loss. One caveat worth stating clearly: this benchmark dataset spans only 2 days of transactions. If we illustratively scale it €600 figure to a full year, it implies roughly 100k euros in annual prevented losses. But I want to be upfront that this is an illustrative extrapolation, not a validated annual estimate, since fraud rates and transaction volumes don't necessarily stay constant across a full year. This answers our third research question: yes, the unified framework delivers state-of-art performance while remaining operationally practical. Let me wrap up with our conclusion and the direction for future work. So, to bring all up together, we present the unified dual framework to our knowledge. First, the joint addresses both class imbalance and the behavioral heterogeneity as single integrated pipeline, then treating them as a separate problems. CTGAN consistently outperforms smooth and Rust across all classifier we tested, confirming that learning through generative distribution of fraud is fundamentally more effective than interpolating between existing samples. Or our UMAP plus DB scan pipeline reveals that fraud is not monolithic. It decomposes into distinct behavioral clusters, and a specialized expert model per cluster captures patterns that a global model systematically misses. And the final system sets a new state of art on the European 2013 benchmark with over 85% cost saving, which is ultimately the metric that matters most in a real banking context. And it's worth emphasizing why this matters beyond the numbers. Preventing fraud reduces not just a direct financial loss, but also chargebacks, investigation overhead, and damage to customer trust. Scaling our test sets, saving illustratively a full year using the EBA ECB 2020 front loss benchmark points to roughly 100k euros in annual prevented losses. Tough again, that's an illustrative projection, not a qualitative figure. There are three directions we plan to pursue. Most urgently, we want to tackle concept drift. Fraud patterns evolve over time, and the developing online or incremental clustering approach without full retaining is a practical necessity. We also aim to extend the framework to real-time stream detection for live transaction environments. And currently, at FIBA we are running an active R&D project on LLM-assisted feature extraction using large language model, the automated feature engineering directly from raw transaction logs. This opens a new direction for how domain knowledge enters the pipeline. Thank you for your attention. My fellow researcher Hakan Hakvar and I will be happy to take any question. Thank you again.
Thank you, Berat. Many thanks for this presentation. There are any questions from the remotely or here at the platea? If not, I have a question for you, Barat. Why, maybe I misunderstood from your presentation or I didn't catch, but why you use, for example, a benchmark that is more than 10 years old, from 2013? There are no new benchmark that can be used, or why you choose exactly this benchmark?
Can you ask that again? I didn't get it right.
Berat, can you hear me? Berat?
Can you hear me? Hello?
Yes.
I didn't get that question right.
Yes, we can hear you,
ask
but
again?
it's, you know. Okay, can you hear me? Or you prefer I write? Benchmark from...
Okay,
okay.
I get it now.
So,
we select the European credit card fraud datasets because it is one of the most widely used public benchmark in fraud detection research. Using these datasets allow us to compare our results directly with existing state-of-art methods under the same experimental condition. Although the transactions were collected in 2013, datasets remains a standard benchmark in the literature due to its realistic class imbalance, large number of transactions, and a well-established evaluation protocol. This makes our results directly comparable and reproducible, I think.
okay. Thank you, Barata, for this, and appreciate again. And if you can send me the presentation, Barata is appreciated because I will collect all of this presentation
Yeah, of course.
together.
I will send
And
in a
then
minute.
send me this. Really appreciated.
Okay.
Okay. Then the next. How can I share from here? I have to share. Okay. The screen.
You can choose here. Is it the PDF?
Yes, it's the PDF.
So maybe this one.
Yes.
This one, right?
Yes, right. Ok. Ok, tutto in full screen, come Ctrl L. Fantastic. So, here we are. Let's see. I'm going to present. Okay. Because my colleague was not here, so but in any case, we did this work together, and I'm going to present the work that we did together with trying to evaluate in a sort of empirical fashion different LLM models in different resources and different hardware, taking into account GPUs and also edge accelerator. Starting from that, okay, starting from that, we try to evaluate not only the performance for running a particular model, but in particular the energy efficient in respect to the model that we have and in respect to the hardware that we have. Try to, let's say, found the difference in between three different GPUs, which are the NVIDIA H100 and A100, and the AMD ML200. And then also we tried not the same model, but let's say analog model also for the Raspberry Pi with the Hilo 10H NPU embedded and running. So basically from that, we try to focus on what? On the energy efficiency by defining unified benchmarking and selecting multiple families for LLM in the different format and try to get the impact of the quantization of this model in respect to the hardware that we have. And we try to explore the feasibility also to use different resources, different let's say, edge computing and low power devices for that. The state of the art. So basically what promotes us to do this activity and to do this work is the fact that in the literature there is, let's say, there are tests that are considering only homogeneous hardware. And this is bring us in order to try to understand a bit better the relation between the hardware and the LLM models that we have. And so basically, we try to define multiple LLM family. We selected multiple LLM families for that. And then we adopt different quantization strategies using heterogeneous accelerators. And this is what, let's say, this is a more, let's say, extended study in respect to what is the state of the art. The methodology. So basically, just to, let's say, make as much realistic as possible, we use 14 different prompts, and we tried to divide, actually we divided the pre-fill and the code phase. And what this was quite interesting, both for the GPU and for the edge architecture. And basically what we did also is find this, take us the opportunity to perform a fine-grained comparison, not only of the performance, but also with the latency, the throughput, and the energy consumption for each device, for each phase, basically. So, as I said at the beginning, 3 different devices were used, at least in this stage, H100, A100, and ML200. And so, to, let's say, start from a as much standardized as possible system, we made use of a virtualized environment. And in particular, we had this virtual machine and container, in particular containerization, where we had the possibility to run all the CUDA stuff and libraries and all the ROCm library and stuff in order to have different separated environment without any, let's say, exchange of let's say, issue and stuff among them. And then what we had is this configuration guarantee us in some way a reproducible environment for testing. Moreover, the Halo platform has been evaluated by using an optimized model that has been downloaded by the model zoo of Halo itself. So basically, we use this model, and for the part related to the quantization, we made the use of aggressive weight for that, and in particular to fit the edge constraint that we have. Some metrics. So all the telemetry from the GPUs and the edge node was basically continuous collected, and in particular the energy consumption has been estimated, not calculated, but has been estimated from the measure of the power and the execution time. And so basically also we get the latency, the throughput, and the token per joule that for each device has been let's say, calculated and obtained. And also, just for a more, let's say, advanced comparison, we get also the GPU utilization and the memory occupancy for the stuff, for the hardware that we have under evaluation. So the model, these are the model when Llama DeepSeek that we have been able to use it. Why? Basically because they are also present in the model zoo of the Halo. So we try to be as much as concrete and reliable as possible in order to have the GPU and the Halo model, let's say, aligned for this. And here you can find the information about the models, not from the model zoo, but from the GPU one. And now let's try to, let's say, have some comparison about the work that we did. In particular, here you can see the prefill and the decode power grouped by the GPU for the different model. Only the GPU, not the edge in this context. And here what we can see is that, so basically, in particular for the decode part, for the decode power, the 800 basically is the, let's say, most, let's say, less consuming in terms of energy. And in particular here for the prefill power, more or less, we are the AMD NVIDIA A100 are aligned. And so the as expected, the NVIDIA H100 is consume a bit more than the rest. This is basically not surprising at all, at least at this stage. And basically the power consumption must be considered not itself, but also together with the energy efficiency. GPU and memory usage. Here we have the first, let's say, understanding that AMD is using a lot the GPU, basically, and this indicates that maybe there is an effective compute resources saturation that may bring also to some problem if you increase the models. Instead, the NVIDIA, both the A and the H, are more or less, let's say, in average using the GPU, even with the difference between the two models. Instead, as you can see from the memory usage here, the 800, for at least for some models, use the memory quite a lot. And this is not a problem for the time being, but for sure, basically, if this can potentially limit the scalability if we are using, we want to use large LLM models, basically. This is something that we have to take into account. Then the throughput. Throughput also for the decode on the left and the prefill on the right, or vice versa, depending on what you see, the prefill on the left, decode on the right. So basically, as you can see, the throughput of the NVIDIA H100 is quite high, at least in respect to some models, and in respect to the two, let's say, GPUs, which are more or less comparable at this stage. And I'm speaking about the A100 and the ML200. But basically, for the decode phase, instead, the throughput is even much higher for the H100 and more or less is almost aligned with the other. So basically, here what we can say is we can say that basically if we wanted to perform, if we want the performance for that, maybe the H100 is what we can, let's say, rely for this, at least for this stage. And then the energy efficiency indicated as token per joule. And here you can find basically that if we have a look to the NVIDIA, we have the A100 and the H100 that more or less are comparable. And if I have to say something, I can say that the A100 is, let's say, a bit more energy efficiency than the major sister that we have, which is the H100. And then, as you can see from here, we did not expect these results, basically. Why? Because the AMD is, let's say, advertised to be low power. But that does not mean that it's also energy efficient for the time being and for the model that we used. And now the comparison with the edge does not mean that it's a real comparison. Why? Basically because in the edge and in the Raspberry Pi, the token per second that are, let's say, run by the edge is less than 40 tokens per second. That means that we cannot have, let's say, we cannot have something related to the streaming, basically. Okay, real-time streaming. This is not possible, obviously. But what we can say here is that if compared with the other, basically, the Raspberry Pi is not bad in terms of energy efficiency. That means that this positioning the ILO 10H for offline, let's say, activity, for offline LLM instead of streaming. That's the point. Then the conclusion, something related as not conclusion itself, but a key message from this study. And in particular, what we have is that the higher power does not necessarily imply lower efficiency. That's the point. In particular, the power consumption alone is not enough to understand what the efficiency of the system and the efficiency of the card. And you have in some way to include the throughput and the energy efficiency in this calculation. Try to be more, let's say, open as possible in order to get the right interpretation to the data. Compute utilization vary across architecture, while memory usage is model dependent, basically. This is not obvious at all, but basically what we get is that the memory utilization most of the time depend on the model that we use instead of the architecture. This is something that is interesting. 800, the NVIDIA 800 as, let's say, can be also obvious, best perform when maximized the inference performance. And this is true when the performance in the inference is your primary objective. That's the point. Throughput is the dominant factor determining energy efficiency, as we have the chance to see from the last slide and from the last comparison with the edge. And in particular, regarding GPUs obviously remain the preferred solution for high-performance interactive inference. But we have to take into account that different GPU, or better, different architecture are suitable for different models. And not there is not an all-in or all-for-one, basically. And then the tiny ILO 10 is not as bad as can be seen, as can be recognized. Why? Because obviously I cannot do let's say real-time inference with this machine, but I can use this architecture for offline low-power deployment scenario, thanks to the excellent energy efficiency if compared with the, let's say, most, let's say, important and named GPUs that we have in this study. So I'm at the end of this presentation, and thank you. Then, if there are questions from the platea or the remotely, I don't see any question from the remote. Someone?
I have a few questions, let's say. One is about the HALO, the AI object for the Raspberry Pi, right? Because it adds it behaves. This is a question. I'm asking, is it similar in behavior like a GPU where you have the CPU RAM and the splitted VRAM of the GPU, and you have something similar in the Raspberry when you put the head on, you have the RAM of the Raspberry and the dedicated RAM of the ILO accelerator?
Yes.
Different in
No, you have.
It's in the same.
It is exactly in this way. So you have the amount of RAM inside the Raspberry, that in this case was 16 giga, something like that. And then you have a dedicated memory in the board of ILO 10, which is 8 giga.
And usually we have a faster DRAM style for the GPU, right? We usually have DDRAM 6 or DDRAM 7 for GPUs. It depends on which one, while usually for CPU RAMs we have DDR4 or DDR5, and I think something similar happens here in the Raspberry. Did you observe any cross correlation between the fact that you have this kind of efficiency per token if you have different, let's say, generation working together or not? But like for DDR4 with DDR6 is better because for versus DDR5 versus DDR7.
As I said, the problem here is that where is here the problem within that, if speaking about the memory, is the model, not the architecture. It seems to be. That's the point. Because at the moment the memory is affected by the model and the amount of quantization or tuning of the model that you have, and not in particular about the architecture. That's the point. And this is, I think that this can be here from the reduce the output. This one. So the part related to the memory in particular. Yeah, exactly. So basically, in particular, we did, to be honest, we did not expect with this kind of memory usage for the 800. That's the point. But, and this is something that is particularly related to the tuning of the model instead of the architecture itself. Why? Because in the case of H800, so some model, for example, the Quen, here in green, basically, is going to use almost more than 70% of the memory. What does it mean? It means that is limiting if you wanted to use a more bigger model with the same family. That's the point. I don't know if I replied to your question.
Yeah, thank you.
So, thanks again, and I move the pen to the next speaker, which is Alessandro Bombini from Italy. And so, wait just a second. He's on, qui dobbiamo close this sharing because it's shared. Okay, and then here we have attack. Select window, entire screen. Allow and comincia da inizio questo sotto. Proviamo. Full screen.
Yes. Can you hear me? Yeah, from here for sure. Okay. I hope I try to be as fast as possible. Hello everybody, I'm Alessandro Bombini from the INFM, and today we present this very peculiar work where we developed a Python library and whose goal is to generate synthetic data for this very specific kind of data, which are so-called macro array X-ray fluorescence, using as seeds a set of RGB images and a set of and a selected palette, and to do that in a very fast way using a distributed computing approach. But of course, before describing that, I need to describe what are X-ray fluorescence macro mappings and why they are relevant, especially for the studies of pictorial artworks, and why we need a distributed synthetic data generation pipeline. Let me start with the stratigraphy of a pictorial artwork. So usually a pictorial artwork starts by selecting a support, usually wood or canvas, and then the artist lie down the preparatory ground using glue and chalk. and then does some kind of white priming where he draws the preparatory drawing, and then starts painting it, putting colored layer up on colored layer multiple times, and then close with a varnish, which usually is organic. And the point is that when we have this kind of pictorial artworks and we want to explore it and to study it, we need to use some kind of techniques. And if we limit ourselves to visible or near infrared, we are able to explore only the outermost layers of this kind of very stratigraphic object. With IR, we can go deeper, but with X-ray and gamma ray, we can actually go all the way through and pass by a lot the entirety of the stratigraphic part of this kind of artwork. And this is let's say the Z section of this object, where we see that we are capable of reaching even after the support with X-ray. So this is why it's relevant. And so how we can extract this kind of information, we take our X-ray, we bombard our pictorial artworks, and then we have some kind of reaction in terms of stimulated emission of light from each of the components here, and we can collect it. And now we can do that. We can do that even with portable, movable, very small objects called portable X-ray fluorescence machines. We have this kind of tube. This is an X-ray tube, and it is solidly attached to a detector in this way. And we can, why it's relevant? Because when we bombard with X-ray anything, okay, we stimulate some kind of emissions called fluorescence mostly, which is dictated precisely by the element species. So it's dependent only on the element comprising the target. And we can collect this kind of raw data, which is kind of images, where we have the X and Y pixel, and instead of having only 3 channels, so the RGB, we have a lot of energetic beams, energetic channels. So we have this kind of object, and we put in front of our favorite painting. We bombard it with X-ray, and we collect the information. We stimulate then X-ray emission from a certain spots. The fluorescence image is collected, and then we retrieve for this pixel. This is the pixel size. We have this kind of signal, and then we start turn on our motors, and we horizontally move, and changing the position, we change the pixels, so the composition underneath it, and we see different reaction signals from that, and we collect it and we store on data on disk. Then, let's say after we have collect for the entirety of our, let's say, subsection of the painting, okay, we convert it through the analog to digital converter and store on disk. And our raw data, which is called data cube, can be explored in multiple ways. For example, we can integrate along a certain energy interval in all pixels and compose an image. This is, for example, the calcium image, where you can see some white spots, probably. Yes, yeah. You can see some white spots there. Or you can integrate around, for example, the LED ones, and you see that there is this kind of correlation between light colors and LED, like for the hand. Or we can compute the iron, and you see we have these different correlations in space, and for the mercury, where the red part is mercury. And you can do it for all the elements or all the channels, and you get this is the actual raw data, this is the data cube. So if you slice it along a selected pixel, you have this kind of spectra, right? Also, XRF is useful because it's a multi-elemental technique that is fast and certain meaning, sensitive, and it is non-invasive and non-destructive, so perfect for culture applications. And as I said, it can be performed with portable apparatus, so you can go in situ, for example, in the museum, or, for example, for analyzing frescoes that you cannot move because are attached to the wall. And also can produce macro maps in the sense of order of meters. And, as I said at the beginning, can explore the entire stratigraphy of the pictorial artwork, so can detect signal coming from hidden pictorial layers. This is just an example. This is a pictorial, it's a painting from an unknown author of 18th century. And looking at an antimony line, you see the emergence of two hidden faces, women faces appearing beneath the guy. And also it's a technique that is available to us. Of course, it has some intrinsic limit. For example, the slow-paced dataset creation, which is the macro one. So, okay, it's fast for the cultural heritage point of view, but it's not fast from the fastly moving artificial intelligence sector, right? Also, we have some kind of noisy data. We need some calibration from ADC to energy channels. We need the data engineering for example, the alignment and resizing over the RGB over XRF. And there's some intrinsic problem like the total detection limits of light elements because its power scales with respect of Z of the element. And more or less is blind to organic properties of pigments in the sense that similarly organic compounds that are always COH may have different appearance, but of course they have the same elements. So for XRF they have the same signal. So the idea is that we can create a synthetic data set for any of our tasks and then perform some kind of unsupervised domain adaptation technique in order to move the synthetic data towards the real data. In this talk, I will briefly present this. So let's say, how can we do that? And the fact is that thinking about how a pictorial artwork is produced, it's easy to understand that the first thing an artist does is that it selects its palette. So of course, when you want to extract an information and reconstruct this kind of information from a pictorial artwork, you ask yourself, how this RGB image, that will be my seed, I want to simulate the XRF of this object, is composed. And they say, okay, I suppose that the red pigment appearing here is cinnabar. Let's suppose the green pigment appearing here is a green hair from Italy, and the blue is, let's say, azurite. And I know that the other elements are all more or less compound. Then from there, I extract information. This is exactly the idea of this tool. So we have the couple. So for each RGB, we assign a palette. A palette is a RGB color. And this XRF signal. So this is the cinnabar signal, this is the green hair signal, and this is the azurite signal. And you see they are different and characteristic, right? And then we cluster to reduce the color space intensity because more or less there's a finite number, right, of color level actually there. For each color, for each cluster, we retrieve more or less the let's say the average color, so the red or this in this case is brown, yellowish, blue, or red or white. And then we check against our database of pigments, the average color of some pigment and its average signal, XRF signal. We compute the colorimetric distance in colorimetric space, delta CLR 2000, between the average color of the cluster and the expected color of the pigment. We compare them for all the clusters, we compute them, and then we compute some kind of similarity between the cluster color and pigment color for all cluster, for all pigments. After that, we use this kind of similarity to define an average signal for the cluster. How? By simply combining them. So this is the signal, the pigment signal here. This is the similarity of this signal with the cluster. And then we have, let's say, some threshold. So we have like not a hard-coded top K selection, but a dynamic tuning of the number of pigments. And this is usually right, then in the sense that artists don't use a single pigment per color, but they use different colors, mixing them together to have their favorite color. And this is what, let's say, simulate that. And then this is normalized in order to define it as a probability function. So this is summed to 1. And we use this kind of distributional probability over the energy space as a seed to have an extraction and compute a Monte Carlo extraction. And you see that n is the number of photons detected in the detector. And when this n increases, its distribution, so the blue samples, which are the drawn samples, approaches the distribution. But in real case scenario, we never reach this very high level of counts. We are always around, let's say, 1,000 counts, more or less, per pixel. And this is another way of injecting noise in our synthetic data set. In this way, we can recover pixel per pixel the data cube. Let's say an example. This is the original RGB clustered. Okay, let's say are the real K alpha potassium line and K alpha copper line. And tuning the threshold, we have different results. So here we have a lower threshold with a higher number of contributions from different pigments, while with a higher alpha, you see that we recover a little bit of this kind of cross correlation between the synthetic signal and the real signal. Keep in mind that we have no clear idea of what is the palette of the artist. So we almost inserted this kind of information, but nevertheless, having this kind of information from historiographic studies, we received that at least in this case, the pigment that are a specific kind of pigments contain this kind of element, and more or less we recover a similar results with a higher accuracy due to the fact that we have a more precise RGB, let's say. If we flatten the data cube along the direction of space, so this is more or less the number of pixels, so the pixel ID, class standard fraternization, we see that, so in this direction we have the energy bins, and those are the pixel IDs. We see the emergence in tan log representation to put more emphasis on some, let's say, elemental lines. We see the emergence of these horizontal lines, which are the elemental lines. And we see that these kind of elements are common throughout more or less all the painting, but we have this kind of emergence here with this kind of localized contribution in a certain region that emerges, and this is more or less kept in the synthetic data. If we then compute the real versus generated XRF histogram at the average section, we see that more or less they are one on top of the other, and we recover more or less all the pigments peaks. Then briefly to the last part, that is, we can generate one of these. Is very slow. How can we speed up? The crucial observation is that generating, if I want to generate, for example, millions of this data, regardless of what I do, this is an embarrassingly parallel task. So I can generate over 1 million nodes and do it more or less in parallel. And so we devise this kind of very complex architecture where we use Dask as a backend running on Kubernetes with a Jupyter Hub and OEDC-based OAuth2O-based authentication system. And the crucial point is that we need a shared network file system, because in this way the user can reach the main node and then dispatch the job to all the Dask computing nodes that simply has to read, which is the image. You see there arrives the image. They read the image. They read the code, they launch the code and do whatever they want, and then they produce the file and store them in the NFS. And so what's next? So we have seen that it's possible to define a pipeline to create a MyXRF data, and simply starting from an RGB seed and a palette pigment. And we can define the whole dataset generation, not for a single image, but for all the images via an embarrassingly parallel job. And then we can speed up the data generation using distributed computing. In this case, we used Dask on Kubernetes, and the code is open source. And then we created multiple datasets using almost all the CC0 Wikimedia RGB images representing pictorial artworks. And for example, the last example is that we get over 300,000 paintings and frescoes images, and we store them on data in multiple formats, and that's more or less most I can obtain it, and it was a quite speed up for the task. Thank you for your attention.
Thank you, Alessandro. Any comment, question from remotely or in Platea? If not, I have one. That is, okay, apart the computational part, which more or less I know, About the technique, which is the real limit of the technique that you show at the beginning?
You mean
of
the XRF?
Yes, the XRF, exactly.
There are crucial issues in the XRF, and this is why usually XRF is used paired with others, because every imaging technique has its own drawbacks and its pros and cons. And as I said, the main limitations are twice. They are not the only ones, but in this case, for pictorial relevance, are more or less the most relevant, since the, let's say, the scattering probability of the fluorescence event is proportional to Z somehow. Is not linearly related, but is proportional to Z to a certain power. It has a higher detection limits, so it excites better, higher, and heavier elements, but it is lower on low detection elements. And also, if you do it in air, you have this kind of wall that is the hair wall that is stronger on lighter elements. So, for example, all the organic elements, and you need something to keep in touch with that. So, for example, using a fluxometer of helium to remove the oxygen from the atmosphere nearby the pictorial artworks. And the other one is that it's a purely elemental map, a purely elemental technique, which means it gives you the elements in the target, but not the chemical composition. So you don't know which, you know that maybe there is a COH, but you don't know which formula of that COH is, so that chemical formula is. And this, especially for all the organic pigments, means that XRF is almost blind to that. So if you have pigments which are similar to each other in composition, in elemental composition, but they may have very different colors, for example. And this is a problem that you usually have to address using imaging techniques that work in a completely different regime.
Thank you, Alessandro.
You're welcome.
Very interesting work. So basically what we have now in the list is Samar. Samar, are you here with us?
Good evening, everyone.
Just wait a second because I'm just trying to this one. Okay, try to share,
Good
Samara.
evening. Yes, I'm ready.
Oh, okay, now I see. Perfect. Put it in full screen.
Sir, I will stop
I'm
this
doing
here.
something wrong. Wait a second. Maybe I'm doing something wrong.
Okay, I will wait.
Okay. Okay, it was my fault. Now try to share, please.
Yes.
Apologize for that.
It's okay? It's okay now?
Now we see yours. Okay, we see the presentation. Okay,
Yes.
we see the presentation in full screen. It is okay. Samara, thank you.
Yes.
The floor is yours.
I beg your pardon. What to say, Mister?
You can start.
Yes. First, I would like to thank the organization of this conference for giving me the opportunity to present our research. My name is Samar Hussam Al-Kayat. I'm a master's student at the Informatic Institution for Postgraduate Study, University of Information Technology and Communication, Baghdad, Iraq. This work was conducted under the supervision of Assistant Professor Dr. Ali Hamad from the College of Artificial Intelligence, University of Baghdad. Today, I'm pleased to present our paper entitled Evaluation of Split Federated Learning for 6G IoT Optimization, a comprehensive study with baseline federate learning, split federate learning.
Wait, Samar, wait a second. So you exit from the full screen.
It's
Okay,
okay now,
now you
sir?
are-
It's okay?
It's okay.
Really, I have a problem with my electricity here in Baghdad is so bad because يعني, I have a big problem because the generator may be shut down at any time. Sorry for interrupt, sir. Okay?
Don't worry. Go on.
Yes, yes. At first, I will ask important question. Why 6G IoT need distributed learning? The next generation of wireless communication, known as 6G, is expected to collect billions of smart devices like sensor, autonomous vehicle, healthcare system, industrial IoT. But this provide me opportunity. It also introduce significant challenge. The first challenge is scale and heterogeneity. The second challenge is privacy and security. The third challenge is limitation, computation. We start to explain each step. At first, billion of IoT devices generate massive amount of data. Sending all this data to a central cloud required high bandwidth, create network congestion. The second challenge may be many IoT applications involve sensitive information such as medical record or industrial monitoring. Transmit all this raw data to a center server increase the risk of privacy leakage and cyber attack. The third challenge is that the third challenge, most of IoT device has limited capability like memory, like a process, because it's battery capacity. They cannot efficiently train a large deep learning model locally. Therefore, we began to start use distributed learning like federate learning, split federate learning. I will discuss now research gap and contribution. At first, no empirical split federate learning or real IoT. No cross paradigm compare between baseline federate learning, split federate learning, and split federate learning based on the one data set and one architecture and one pipeline. Now I will discuss the three distributed learning paradigm. At first, federate learning. Federate learning means that the client train the full model locally. Only model weights or gradient are sent to server. And then the server do the aggregation them with federate average. We can see it in the left part of the figure. Split learning, the network is split. The first layer that clients execute and the second layer that the main server execute in order to reduce the computation. My work begin to combine the advantage of federate learning and split learning. Now let's discuss about briefly understand the data set and the pre-process that I do in four paradigm. The data set contain 1,000 sample and 21 input feature. The prediction task is binary classification. That means I have two class, optimize or not optimize. At first, we must do some pre-processing. Missing value and duplicate record were removed. I do numerical feature were normalized, while categorized feature are encoded. The data set is divided into 70% training, 50 validation, and 50 testing. using stratified sampling. One important issue that dataset was imbalance. Mean that 83% of sample belong to not optimized class and 70 belong to optimized class. To avoid bias learning, random oversampling was applied only to training data sets. On the other, validation, there is no modify invalidation or test dataset to prevent data leakage. Um, now I will discuss the architecture of the model that I use for in 4 paradigm. Every paradigm use the 8-layer DNN uh, with the 50 neurons, and I use binary classification. Therefore, I need sigmoid optimizer, sigmoid activation function. Sorry, each hidden layer use the ReLU activation function on the sigmoid because it's binary classification. Here I put some hyperparameter I use in my work to improve generalization and reduce overfit, like dropout with 0.4 together with L2 regularization, and I use Adam optimizer 0.001 and binary cross entropy as a loss function. At first, I take the result of test accuracy in this figure. Because the dataset was unbalanced, the accuracy is not give us the full picture. We need another matrix like a precision, recall, F1 score. At end, as a conclusion, we observe that split federate learning achieve the highest precision and highest recall and highest F1 score. These results indicate that split federate learning provide us the most balance and detect the minority optimizer classes. Therefore, split federate learning achieve the highest accuracy and the balance between computation and the balance between computation for IoT device. I will discuss the future work. Sure, I need to scale many heterogeneity clients, a large or diverse 6G IoT. Well, maybe in the future work I can add, or any authors after me can add differential or cryptographic generity. Thank you for attention. I'm ready for any question or discussion.
Thank you, Samara. Very appreciated, and thanks also to stay within the time. There are questions from the platea or from the remote for Samara. If not, Samara, I have a question for you.
Yes,
And
I read.
the question is how you plan to implement the part related to the security. I mean, the security intended
Yes,
as
yes,
a
yes.
slide
Yes,
in the
yes,
future.
yes. Security or privacy is not my aim. I build the framework that involve provide to us privacy or security, because at first I will keep every client with own data. Okay, this automatically provide security or privacy, and I will not send the raw data through the clients. I split the model between the client and the server, and this procedure maybe reduce the attack or cipher. Therefore, I work privacy and security in design, not by using methods like cryptography or like any differential method. This is the core of my work.
Mhm.
Yes.
Okay. Thank you. Thank you again, Samar. Very interesting and appreciate really. Thank you.
Thank
Many
you.
thanks. And let give me the opportunity to thanks all the speaker of this afternoon session and the valuable work that you did for this and for this workshop and for the activity of this workshop. If you don't mind, I kindly ask all the speaker, if you did not already done, obviously, to send me the slide of your presentation, maybe in PDF or whatever you like. And I wanted to collect them together and put within the web page of the AMDA workshop, just to collect them and let's say to be shown to the rest of people that maybe today cannot let's say join us in this activity. Many thanks again to all the speakers for the valuable work, and also this is not trivial to be on time, and so I appreciate really. Thanks again, and I don't know. Let's have a look for the next year, depending where the conference will be. But I hope to see you next year for the prosecution of the workshop. Thank you again, and see you.
Thank you.
Okay. No questions online, right? We can move on. We are, yeah, it's 4:20, so let's continue. Yeah. Okay. No. Okay, so you have to share it every time. Okay, yes. Okay, so the next speaker is Johanna Korstel from the Center of Mathematics of the University of Minho, and she's going to present the work recurrent neural networks for predicting inflows in hydroelectric reservoirs.
Thanks, Cecilia, for your presentation. This is a joint work with Emanuela, Cecilia, and Emanuela from University of Minho, this is a student, and Cecilia, that is on the Schmidt University, and Luís Ferraz from University of Minho. Okay, this is outline of my talk. I will start with a brief introduction about hydropower and its essentials, motivation, and goal of this work. Then I will present our case study, and then I will present numerical networks for inflow predictions and the results, and this presentation with some conclusions and future order. So hydroelectric power is a major renewable energy source, but dam constructions profoundly alters river ecosystems, landscapes, and socio-economic dynamics. It affects the biodiversity by modifying fish habitats and reducing species richness, which can lead to decline of or even extinctions of certain species. The local communities are also affected by this, with consequences as decline of fisheries and loss of livelihoods, reduced water availability for agriculture, and also increase the competitions for water uses across energy production, irrigations, recreation ecosystem. So sustainable hydropower operations requires balancing among electricity productions, ecological flow requirements, and agriculture water allocations. Existing AI-based approaches for hydropower management namely focus on maximizing energy productions without explicitly considering ecological flow requirements and water allocations for agriculture. So in this work, we address the predictions component of a hybrid framework that combines neural networks for reservoir inflow forecasting and constraint optimization for hydropower management. So the goal of this work is to develop and evaluate neural networks models for accurate hourly and daily inflow forecasting. These forecasts are used to support downstream optimization. So accurate inflow predictions is crucial as it provides information about future water availability and enables more efficient management of current and future water resources.
So our case study is the Miranda hydroelectric plant. This plant is located on the Araguari River in the state of Minas Gerais of Brazil. We select this plant because it provides public available hydrological data for this period year, 3 years, 2021, 2023. The main characteristic of this plant is this year. This reservoir has an area about 51 square kilometers and a usable storage 1.1 cubic meters, and it has an installed capacity of 408 megawatts, generated by 3 Francis turbines. This data set contains more than 26 hourly records from this period, and this original data has 18 variables. In our case study, only consider these 2, the timestamp, this variable dim instant that has the year, the month, day, and the hour, and the variable vazão fluent that is the reservoir inflow. The prediction task is to forecast future reservoir inflows at hourly and daily time scales. And this figure here, we show the hourly flow times series for this period. We do an exploratory data analysis. From the data quality analysis, we identify one missing value and also more than 1,400 negative values, which physically are impossible, that doesn't have any meaning, and we remove this. And at the left, we show the blocks plot of the reservoir inflows. As you can see, it has a strong right skinned with a compact interquartile range. It also has high value outliers, more than 3,000. These values correspond to extreme inflow events associated with rainfall and seasonal hydrological peaks, as you can see from this box plot. So you also do a data cleaning of the data set. We test several imputation strategy. These are some of them that we test. From these the tests, we conclude that the median imputation exceeds the lowest mean X square error for inflow predictions. So in our the clean data set, we adopt by this imputation. So we replace the non-val and negative values and outliers with the median. So we construct this clean data set, the data set H, hourly inflows. From this data set, you also create a daily data set obtained by aggregation of the data of inflows using a day sum. And our objective is to predict future reservoir inflows at hour and daily resolutions. Next step, we analyze the temporal dependency of the data to determine the appropriate input lag. This is the number of the past observations used as model inputs. So the autocorrelation functions measures the dependency of a time series with its own past values. From this test, the results for data set, this shows that the strongest autocorrelations occur at lag 1. So indicated the inflows, the inflows are highly dependent on the previous day. We also do a partial autocorrelation function apply that measures the direct relationship between time series data and its lag values, removing the effect of intermediate lags. And these results here for data set D show again the strongest partial autocorrelations at leg 1, which confirm that this leg is the most relevant. So in our next, we consider in our work, the previous day is used as input to predict the inflows at the next day. So you also apply a pre-processing techniques. Several pre-processing techniques were also tested to improve the performance of the neural network models. We test these ones here, and from these tests we conclude that normalization to the interval 0-1 consistently achieved the best predicted performance, and was therefore adopted in this work. So we evaluate 3 frequent neural networks, a simple RAN, ALSTM, and GRU, with different network configurations with the number of the layers, or route, learning rate, activation function, and weight initialization. We split the data set in 3, 8% for training, 10% for validation, and 10% for testing, where the chronological order was preserved in this split. All architects were evaluated, trained with hourly and daily data sets, but the hourly data yield poor generalization performance due to short-term fluctuations, high noise, and irregular hourly variations, result in less stable model trainers. Because of this, we focus our analysis only on the daily data. The models were training using this configuration here, the Adam optimizer, a batch size of 64, a maximum of 100 epochs, and we use also a yield stopping. We consider a forecasting horizon of 7 days using the recursive strategy, where each predicting flow is used as input to predict the next day. These are the results with the data set, the daily data set for the three neural networks. We show in the last 2 columns the root mean square error and the mean absolute percentage error. As you can see from this table, the GRU model achieves the lowest prediction error. So we will adopt by this model, and this architecture it has 1 GRU layer with 100 neurons and 1 dropout layer with a rate equal 0.1. So we also analyze the train process. In this figure here, we show the training and validation losses, and as we can see, these losses decrease rapidly during the first epochs, indicating that the model learns effectively from the data. After approximately 4 epochs, improvements become marginal, and the curves remain very close each other. So this behavior suggests a good generalization for this model and no clear signs of overfitting. The yield stopping terminated the training after 12 epochs. Here we show the results for 7-day forecasting. The GRU model, as you can see from that table here, the GRU model accurately follows the observed values quite well during the first 4 days. On day 5, the observed inflow exhibit a pronounced peak that the models fails to capture. Since the forecasting strategy is recursive, the predictions errors are propagated to subsequent days, leading to accumulated errors. Nevertheless, the Guru model provides a reliable short-term inflow forecasts and is suitable as the predictions component for our hydropower management framework that we intend to implement it. So, conclusions of this work. This work demonstrates the feasibility of neural networks-based inflow predictions for these plants, the Miranda hydroelectric plants, using 3 years of hydrological data. The daily data, the models trained with the daily data auto-performs the models that are trained with hourly data to predict. Among the test models, the Guru achieves the best results. For 7-day forecasts, the model with the 7-day forecast capture channel trends, but struggle with abrupt peaks events due to the recursive error accumulation. So due to this, our future work is to improve the peaks predictions using hybrid architectures, such as attention mechanisms, CNN combined with LSTM, extended forecasting horizontal controlling error propagations, and we aim, as I said, integrated the predictive model into constraint optimization framework for sustainable hydro operations. So this is our work, and these are some references using this work. And thank you for your attention.
Okay, we have time for some questions. So, any questions?
You have several outlines.
Many outlines, more than 3,000.
You have replaced them by the min?
By the min.
Is this usual?
This is the imputation that we have more the best results with the neural networks that we have. We do some combinations. We test some of these imputations, but at the end we have more the best results with the median imputation, as you can see here. It is a strategy as others. We replace the negative values with 0. We replace outliers with the mean of the neighborhood values. We replace outliers using this function here.
What does it mean, a negative value here?
It does not make sense in our case because it is in flow. Yeah. So we replace this by with some strategy here, but we replace at the end the best result with the median. Yeah.
Okay, let's thank our speaker again.
Next.
The next presentation is on us.
Are we good on microphone?
Yeah. I'm checking on my phone.
Okay, so the next presentation is by Rui Vaz from the University of Porto, and he's going to present about parameter estimation for a spring pot fractional dashpot viscoelastic model.
Optimization and numerical Laplace inverse. Okay, Celia, thank you for the introduction. Welcome everyone. So the outline, I'll start with a brief introduction to the origins of fractional viscoelastic models. Then I'll move on to fractional viscoelastic models of the single order and the new viscoelastic model proposed in this work. And then I will introduce how to perform fit to experimental data, and I will end with the conclusions. So introduction. Here you have a picture of Nutting. In 1921, Nutting wanted to generalize the idea of viscoelasticity, or he wanted to model viscoelasticity. So on one hand, he had a purely elastic behavior, Hooke's law, which is represented here. So here sigma stress is proportional to deformation. Back then they would write in this way. And on the other side, you have the purely viscous behavior, Newton's law, where the stress is proportional to the, not the deformation itself, but to the rate of deformation. If you don't want to use the derivative, you can write it in this way. So he wanted to find a way to characterize materials that are neither modeled by Hooke's law and neither by Newton's law, viscoelastic materials. So his idea is to present a mix of that previous two formulas here, given by in this way, so where A is a parameter of the model, M and N are the exponents, and of course we can see that we can recover the previous two formulas by playing with this M and this N. He could obtain, for example, a fit to experimental data. He could easily obtain with this formula here, with this 0.28, 0.2, 0.56. For a hard steering pitch. He commented on the work of Maxwell, and Maxwell presented in 1867 this model that I will explain now. But he was not in favor of Maxwell's work. So Maxwell basically had a spring connected to a dashpot in series, like you can see in this model here. So for the spring, we have Hooke's law, meaning that the stress that we'll feel in our hands will increase as you stretch the spring. And when you have the dashpot, stress is no longer proportional to the deformation, but to the rate at which you are deforming, meaning that if you try to open this dashpot really fast, it will be impossible. It will block. So assuming that we have this model, and that the total deformation of this model is the sum of this deformation, which is this gamma E, plus the deformation of this model, gamma F. If you combine them together, and if we derive on both sides of the equation, we arrive at Maxwell's model. This combination of these two constants is called the relaxation time, and this one is the viscosity of the model. But nothing would complain about this model, because you would say that, okay, the model presented by Maxwell may be nice, but it's only nice in certain regions of the spectrum of viscoelastic behavior. So nothing really believed that he could model the whole spectrum with a different law. At least he was trying to do that. Later on, we have the works of Scott Blair, and Scott Blair tried to do the same thing as Nutting, but he was not aware of his work. So we presented basically the same formulas, but in a different way. So we have this is the same formula we saw before for the Newtonian law, and this one for Hooke's law. So he has these two characteristics, the one viscosity, this one is called shear modulus, and you wanted to obtain an intermediate characteristic here. You can see that the difference from this formula to this formula is that we have a t here, and here we have t to the power of 0, for example. So he presented this formula, and he said, this will be the intermediate characteristic that I'm going to use to model viscoelasticity. And he called this firmness coefficient. He was working with psychophysics, and he would in his papers, he gathers a bunch of people, he gives them samples of viscoelastic materials and asks them to press the materials between their fingers, and then to evaluate the firmness of that materials. And he could find a really good correlation between what people used to say, okay, this is 10% softer than the other one, something like that, between this formula he proposed and the psychophysics results he obtained. Later on, he introduced a different idea. He stopped working with the previous idea, and he said, okay, this is the same formulas that he was showing before. I have this relationship with this property, this viscosity with this relationship, and these shear modulus with this relationship. And the main difference is that I have a derivative of order 1, and here I have a derivative of order 0. So he introduced the idea of using a derivative of order between 1 and 0, or 0 and 1. Although he was not still aware of these fractional derivatives. But his idea was this one. Okay, I have here some fractional derivative. I don't know what it is yet. But when this is 1, I obtain Newton's law for fluids. When this is 0, I obtain Hooke's law. So now I have to introduce fractional derivatives. And fractional derivatives, it all started in the 17th century when Leibniz proposed this kind of formulation. Okay, the nth order derivative, and then L'Hopital replied asking, what is the meaning when this is equals 1 divided by 2? Okay, basically to introduce, we just want something that can behave as a derivative and is not of order 1 or order 2. So we start with the fundamental theorem of calculus. And it is well known that if we derive this capital F function here, we will obtain this f, the integrand function. Now let's define the n-fold integrates and the n-fold derivatives. Imagine that you have the integral of the integral of the integral. We just use this notation Jn. And if we have the derivative of a derivative of a derivative, we just state the n. We have this lemma that says that if we apply n times integrations, we don't need to use n time integrals. We just need to use the symbol of integral 1 time, but we need to use this factorial. So we don't have derivatives, but we have integrals now. So if we want to perform an integration of order 0.3 or 1.7, the main difficulty is found here. Otherwise, we have no problems in this part of the formula. So we need to replace this factorial, and this can be replaced with something that generalizes factorials, which is the Euler's gamma function. And using this relationship that n minus 1 factorial equals gamma of n, we can write a generalization of the integral. Okay, and this is called the Riemann-Liouville fractional integral. Now, the idea is that, what about the derivatives? So to obtain derivatives, we're going to do something really simple. We're going to use always integrals. Our derivatives will use integrals, but we will perform the mth derivative of the Jm minus alpha derivative, where this m minus alpha, it's something non-integer, okay? So it's basically, I have a derivative of order 2 of j something 2 minus 0.1. So we will obtain a derivative of order 0.1. Or we can do the other way around. We apply first the integral, we apply the integral to the derivative, and then we see that the derivative here was outside and here is inside in the integrand function. These are two classical fractional derivatives used in literature. In our case, we're going to use this one, which is called Caputo fractional derivative. Just for you to have an idea, since we were talking about derivatives of order between 0 and 1, this is the formulation for the Caputo derivative. We see that every time we need to perform a derivative, this is a non-local operator, we need to compute always this integral from 0 until the time step we need to study. Now, fractional viscoelastic models, as Scott Black proposed, the first viscoelastic model, fractional viscoelastic model, was this one, where we have the stress is proportional. This is called a quasi-property to the derivative of order alpha. As I told you before, if alpha equals to 1, we obtain Newton's law. If alpha equals to 0, we obtain Hooke's law. And this is called, in the literature, they call it a spring pot. It's a mix of a spring and a dash pot, I believe. So the mechanical analogy for this spring pot is this one here, where we have this complex combination of springs and dash pots. And one thing to pay attention is that here we have a spring, meaning that this model will always show a more solid-like behavior, not fluid-like behavior, and we would like to have a fluid-like behavior. So the next thing to do that we can find in the literature is the fractional Maxwell model. that we're going to combine two elements, and that two elements are these two spring pots. We have one spring pot with ordered alpha, another one with ordered beta. We combine them in series. We assume that the deformation of this one plus this one gives the total deformation, and we obtain this quite similar equation to the classical Maxwell model, but now the derivatives are fractional derivatives. So, what is the problem with these models? Both of them show a more solid-like behavior and would like to model fluids. And for that, we created a new model. So the idea was to use something that is already known. It was published in 2018, Yao's fractional dashpot. If you take a look, it's quite similar to the spring pot, but now there's a difference. Instead of, we have a combination of springs and dashpots, but instead of having a spring here, we have a dashpot. So meaning that the fluid works like the model works for fluids. Okay. So in order to have an idea, this model, I will show the model in the next slide. It has a parameter beta. When beta equals to 1, we obtain a dashpot. When beta equals to 0, we obtain the Maxwell model. So it lies between this dashpot and something between the Maxwell model. The model, we just need to have a look at this last equation here, and you can see that the stress equals something, and besides this exponential function, if we remove this exponential function, we would have the Caputo fractional derivative. So although the author, when he published the work, he was not aware of the name of this fractional derivative, this is a temperate fractional derivative because we say that this singular kernel is temperate with this exponential. So it's called temperate Caputo fractional derivative. But the author was not aware, but he was using this fractional derivative. So the new model we propose, it looks quite similar to the previous ones, but now if you take a look, we have here a spring pot, you see a spring, and we have here the fractional dashpot, you have a dashpot. And we always know if we have a dashpot attached to this end, we always know it will have a fluid-like behavior. So once again, to obtain the model is this one, okay, I will explain in a bit. Again, we assume that the total deformation of that model comes from the deformation from one spring pot and the deformation of the fractional dashpot. And the final model is this one here, okay? So now, supposedly, we have a model that would be better than the previous ones. We don't know, I'll show you later. That could model viscoelastic behavior, okay? So now we're going to perform fit to experimental data. And how does it work? We're going to perform fit to different sets of data, okay? This one is called the small amplitude oscillatory shear, and basically we have two parallel plates, one plate on the bottom, and then we put a sample of material, viscoelastic material. And we want to characterize that material. So what do? We press that material and we rotate the top plate. Let's say we rotate 30 degrees and we change the velocity we rotate. At each time we rotate, the viscoelastic fluid, since it has springs inside, it wants to recover its original position, but it will never be able to recover the full position, the initial position. So we say that, let's say that we rotate 30 degrees and then it recovers 10 degrees. So these 10 degrees we recover, we call it storage modulus. It's related to the spring. And that 20 degrees that we missed, it's the energy that we dissipate, we call it loss modulus. And these two values can be, this characterization can be performed in a lab, and we obtain for each velocity of rotation, we obtain a pair of G prime and G double prime. And we can also mimic this and try to mimic imposing this deformation here, which is the sine function. We can mimic this and impose this deformation in our model. No, it's not this one. In our model, and try to get some expressions for the G prime and G double prime. And the expressions are given here, so we don't need to pay so much attention. But we have expressions for these G prime and G double prime. There's another test that we can perform, which is this one here. So we have a spring and a dashpot, which represents the material. Okay, we stretch the material and then we stop. We make like this. We stretch, we stop. And then inside, imagining we have springs, the spring will try to recover its original position, and the dashpot will allow this distribution of the spring to its original position. This measures the stress felt in our hands when we stretch it. And you can see that the moment we stretch, the stress is really high. And as time goes by, the stress goes to zero. This stress divided by the deformation we applied here in the first instant gives the relaxation modulus. It is possible to obtain this relaxation modulus with this really complex expression, but it's quite easier to compute this relaxation modulus using an inverse Laplace transform, which we cannot obtain this inverse Laplace transform, so we will do this numerically. So, how to perform the fit to data? We have two data sets. So the first one is storage and loss modeling, and we have the one from the relaxation modulus that I showed you before. So we will divide this optimization or this fit to data into two different steps. So we want to minimize the error, and this error here is obtained as the sum for the different experiments we perform using the values from the model and the experimental values. We want to minimize that difference. So this will be problem one, and after problem one, we will obtain the model, the parameters of the model that will be used as initial guess for solving problem two. Problem two will consider the full spectrum of data that we have. So problem two, it's quite similar to the previous one, but now we have the data from G prime, G double prime, and the relaxation modulus. And the initial guess will be given by the results we obtain in problem one. So how to solve this problem? Problem two. So we have the initial guess. We use the Talbot method to obtain the inverse Laplace transform. Okay, so we have not G prime. So we have the relaxation modulus. Then we have problem two itself, and then we have to meet some stop condition. If not, we use this sequential algorithm to solve our problem. Here are the results, the fit to experimental data. Each set that you see of this G prime and G double prime represents a rotation with increasing velocity. Frequency, increasing velocity along this axis. And you can see that we obtain a really good fit to the experimental data. This is problem one, solving problem one. And solving problem two, this is a relaxation modulus. It's a fair fit. It's a good fit to the relaxation modulus because we also have some deviations from the experimental data. So how did we perform this? Problem one was implemented using AMPL without pre-solve, and the optimization problem was solved using the IPOP solver with default parameters. For this experimental data, after solving problem one, these were the values we obtained for the parameters of the model, and this was the error, considering only that set of data. And the optimal solution was achieved after 16 objective functions. All computations were carried out using the free NEOS cloud computing service. Problem two was solved and implemented in MATLAB, where we use routines for the Talbot method, and the optimization was performed using the fmincon function with the interior point algorithm. And the optimization converged that one in MATLAB after 10 iterations. These were the final parameters, and this was the final error for problem two. Conclusions. So basically, we proposed a new viscoelastic model. It shows fluid-like behavior as we wanted. It allows a better fit to experimental data, although I do not show that results here. And we performed fit to data with some optimization procedures, and it showed superior fitting accuracy, as I told you before. So these are the acknowledgements and some bibliography, and thank you for your attention.
Okay, we only have time for one really quick question, if there is one. If there isn't one. Why can't beta be bigger than 1?
Bigger than 1?
Mm-hmm.
The model was derived just considering 0 and 1. It was forced by construction to be between 0 and 1. If I use a value bigger than 1, I don't know, it doesn't make sense or in the model. But because it's the house model, it's not our model.
Okay. Okay, let's thank our speaker again. Now we have two virtual sessions. The first one is Alexandru.
Yes. Hello. Good evening. I hope you can hear me well.
Yes. Can you share your presentation?
Yes, of course.
Not
So
yet.
in a second, let me know when you see it. Is it visible?
Yeah.
And
Yeah,
I'm
yeah.
audible. Yeah. Okay. Let me start then. You can stop me if we lose connection or anything. So good evening, everyone. My name is Alexandru Dinu, and I'm going to tell you more tonight about chaotic system fingerprinting for cryptographic key stream attribution, a deep learning approach. This paper was prepared together with some colleagues at the Politehnica University in Bucharest, Sara Modan and Madeleine Frunzete. On the next slide, we can see what we are going to discuss about. So first, it's about motivation and what is our problem, what are we trying to achieve. We studied 4 chaotic attractors. I'll tell you in a minute more about them. We generated some data in order to draw some conclusions. We pre-processed that data, and then I'll introduce what deep learning methods or framework we used. We will have a look at the results for binary and 4-level quantized sequences. I'll tell you more in a minute what those are. And we will see that high entropy is not always a solution or a guarantee that fingerprinting or system identification can be prevented. And we will conclude and we will see what are the security implications and the learnings after this discussion. So the aim of this paper or the aim of this study was to check and to demonstrate that deep learning can identify a chaotic system and can really point and say this sequence or this data set is created by system A, B, or C. This can be something that can be missed, let's say, by other randomness tests. So this was our aim, our goal. The hidden assumption in chaos-based cryptography. Chaos-based cryptography, it's that part of cryptography which is based on chaotic systems. So as I mentioned, we will see 4 of these chaotic systems tonight. And the hidden assumption in this domain is that when we notice a key stream, so a sequence of bits if you want, it doesn't tell us anything about the chaotic system that generated the sequence of bits. And we want to see if that is true or false. So this is our hypothesis to check or to validate or invalidate. The chaotic systems we checked were Lorentz, Rössler, Sprott, and Henon, the 3D version of Henon. They are widely used in the literature as entropy sources to generate keys for cryptographic purposes. And today, security evaluations rely on statistical tests based on entropy or NIST tests, and not so much on resistance to attribution attacks. Why is this whole discussion that will come next relevant? If we find a classifier, or if there is a classifier then that can identify the source, the system that generated a specific sequence of data, then the attacker has a concrete advantage. So they can exploit the system-specific statistical weaknesses, they can estimate parameters, and so on. In cryptography, most of the times, these assumptions, or let's say this statement, it's kind of assumed as known. We know the system, we know everything about it, but we went a step before that assumption, and we really wanted to see how an attacker can learn a system just looking at a short and maybe even binary sequence of data. So this is the research question: if a deep learning model can identify the source attractor from this short sequence of data and quantized, as I mentioned. These are the attractors we studied. So we have the Lorentz system, Rössler, Sprott, and Henon 3D. These are the attractors. So you notice here how the states evolve in X, Y, Z because they are all 3-dimensional. The first 3 are continuous systems. They are defined by this deterministic set of equations with specific parameters. for example, Lorentz has sigma, rho, and beta, some standard values in the literature, similar to Rössler, Sprott, and Henon 3D, which is discrete. What we've done next was to initialize our systems. So we started from 1,000 independent initial conditions, normally distributed, 0 mean, and 1 as a variance. And we have here a tree because it's XYZ, as you've seen before. We use MATLAB as a development environment, but the same results, of course, can be obtained in any environment like Python, C++, or anything. And we generated sequences, iterations of data starting from our initial conditions for all systems. We then removed the transient time, or let's say we didn't consider the transient iteration. This means that at the beginning, all these chaotic systems need some time to stabilize. So you will see a lot of variation. The histograms, the probability density functions of the data are very volatile. And after some time, they stabilize, and we can work with that data, or we can use it for statistical or other conclusions that we want to draw. And you notice here that depending on the system, this transient time is different, from 20 seconds to maybe even 100 or 1,000 seconds for Henon 3D. This also gives you an indication how difficult it is to obtain data, because if you need to wait 100 seconds, which of course quantifies in a lot of iterations, to start using some data after moment 100, well, that's quite a lot, and maybe you don't like that, and Lorentz is a system to prefer. And then we also analyze these systems from a statistical independence point of view, because most of the times in pseudo-random number generators applications or cryptographic applications, we are interested in how do we select independent data or pseudo-independent data. And we've applied the UV-like scatter chi-square test. And these are the durations in time we need to jump, let's say, between iterations such that we guarantee that we obtain independent data points. As you notice here, these jumps are also different depending on system. Next, we quantized our data points, which are real points, because if you look on the previous slide, we don't have any guarantee that these are integer numbers. Of course, we get numbers between -20 and 20, for example, for Lorentz. So we quantize them on, let's say, 2 levels, 0 and 1, or 4 levels, 0, 1, 2, 3. We took a threshold. Usually it was the mean, it was the middle point, like 0 in this case, and it's easy to quantize the data. What we did next was to input this quantized data into several neural networks models. And we had a dense, simple network here. We had a CNN, a light with quite a lot of parameters, as you notice. We had the ResNet baseline and the ResNet robust, as it's called here. It's different from this one because it also adds some Gaussian noise to the input. And the aim, let's not forget it, was can we identify the system just looking at this quantized data, and how can we do that? You can see on this slide confusion matrices and results, high-level results obtained for the 4-level quantized sequences. So in most of the cases, the ResNet baseline and the ResNet robust versions, variants of the networks used, gave us quite some good estimations of the systems, so more than 90%. The CNN light and the simple dense network was slightly slower than this, slightly lower than this. But of course, it comes all with a price because we have quite a huge number of parameters, and also the simulations we did took quite some time. But the good thing is that we are able in 92-93% of the cases to tell that the Lorentz system was the one that generated the specific sequence of 4-level quantized data points. We can have a similar view or a similar analysis for the binary quantized data. And you notice here that the percentages are slightly lower than before, not more than 90% now, it's around 86%. And of course, the CNN light and the dense simple are even lower, around 60%. One could ask himself or herself, why do we have this difference? Well, potential answer could be that when we quantize the data as we did on the previous slide in 4 levels, and of course if we go to 6, 8, or 16 and so on, we kind of include a bit more information, and the neural networks can see these patterns, these trends, and can identify the systems more easily than in the binary setup as it's shown here. On the next slide, we also had a look from an entropy point of view, because sometimes we hear a lot that, of course, we have a source with a high entropy. This is a great thing. We can maybe not identify the system, or it's great for application for cryptographic purposes. And as you can see, the Lorentz system has a quite high entropy. Rösler, very similar. Sprott, not so good. Hennen, also high entropy. And we compare the entropy values with the F1 score obtained on the previous slides. So statistical randomness, let's say, doesn't mean anything in terms of fingerprinting or system identification. Because usually standard tests, like we mentioned, entropy tests or NIST, they capture frequency and uniformity of data. But deep learning, as we've shown on the previous slides, of course, can see sometimes a bit more, which is not so much visible to the naked eye or to the unexperienced user, and can see temporal dependencies or structural signatures that other tests ignore or don't observe. Why is all this discussion relevant in the end? Well, because if an adversary, if an enemy, if you want, intercepts a key stream and trains a classifier like we did on known candidate systems, known candidate attractors, known candidate chaotic systems in the end, you can easily identify, or let's say with a high probability, you can identify the source system. And you can apply targeted cryptanalysis after all, and you have an easier job to break that system and that cipher. So it's really important. Some of the recommended countermeasures are basic, you will see, but now we have really good reasons to, just to mention them again. So post-processing is important. Hashing to the key stream is important because it removes the signatures, and the output is more indistinguishable, let's say, from noise. If we use a single discretization scheme like we've seen before, either binary or 4-level, can give a false sense of security because it can be, it may seem safe to use a system under the specific quantization, but it may be not so safe, or the system can identify the system on a different level size. Usually it could be an idea to have a hybrid scheme. So maybe combine more systems, cascade them. It's also an alternative and something to consider. And of course, if we use initial conditions one time, or we change them very rapidly, that's, as usual, a very good approach. I'll get quickly to the conclusions. So the ResNet robust variant of our network identified the chaotic systems with quite a high accuracy, 92% for the 4-level quantized sequences, and almost 90%, 86% for the binary ones. I forgot to mention, I didn't mention that the sequences were quite short, 150 time-step sequences. Second, high entropy does not guarantee that we cannot fingerprint, we cannot identify our system based on machine learning algorithms, and we've seen this in this paper. And of course, regularization is decisive. I didn't go so much into details, but similar networks or identical networks can give a lot of difference depending on how they are designed, just minor differences which make a big impact. Discretization schemes, you've seen, they are important, binary, 4 levels, and so on. So we have to validate across multiple schemes before getting to a conclusion. And we can use this approach, this framework, this methodology, of course, in order to do kind of a pre-assessment of any system before saying it's a good system. And it can be, added to a battery of tests if you want. So it shouldn't be used alone, but it could be a good addition to a tool set of cryptographic enthusiasts. That's it. Thank you very much for your attention. I'm open for questions if you have some. Thank you.
Okay, we have plenty of time for questions. So who has a question? Okay, maybe I'll start. So I'll start with, so I've never heard of ResNet. Can you hear me? Well, yeah. Can you hear me? No?
Yes, I can hear you well, yes.
I've never heard of ResNet Robust. So you said it's a ResNet with noise.
Yes,
Where
yes.
is the noise added? Is it on the skip connection?
Yeah, we added noise on the input, so we really added noise on our data in order to, you know, artificially make it less, let's say, less the same as it's coming from a chaotic system. Anyway, chaos, you know, whenever you have a small difference in the initial conditions, it creates chaos afterwards. So we wanted to see what happens when we just change a bit, artificially change our input, and just train the ResNet based on that. And it looks like in some cases it helps. So this robust is just a term we put here, but it's a ResNet in the end. We just discussion noise at the input. Yeah.
Okay. So the architecture doesn't change. Okay.
No, exactly.
Okay. Anyone got a question? No? Okay, so have you heard of physics-informed neural networks?
Can you tell me again the term? I'm not sure if I got it. Physics?
So physics-informed neural networks. So they are a neural network that incorporates, so since you are using physics systems, so you know the equations that are generating the data, physics-informed, you add the differential equation to the loss. So you are sure that the neural network is learning the physics. Instead of trying only to learn the physics from the data, sometimes it's hard. I don't know if you tried some extrapolation experiments. So for example, trying to predict with your ResNet beyond the training time.
We did. That's in another paper we presented at another conference, and indeed it was quite interesting because we managed using again a setup of neural networks to simulate something which was very close to a Lorentz. Let me go to this slide. A Lorentz attractor, but it was a different Lorentz. So this was really interesting based on the parameters that the network learned indeed from the data. We generated a different chaotic system, which was kind of parameter driven. But it's a good point that you mentioned with that with the physics part, because we didn't consider that until now, and I think it's good to look at that, especially because the systems kind of show that appeal. You're right. Yeah. That's a good point. Thank you.
Any questions from the audience? No? Then I'll continue.
Thank you. Just one question from my side. Do we have to share the presentation with you or anyone else?
Did you show your contact at the end?
I think I showed it at the beginning here.
Okay, so if anyone wants the presentation, you can just send an email, right? Yeah.
Clear.
Okay, so
Thank
one
you.
more question. How did you optimize? So you compared a CNN and two ResNets. How did you choose the parameters for the neural networks? Did you use some kind of optimization process previously, or did you just randomly choose the parameters like the number of neurons, number of layers, and so on?
Yeah, it was just that indeed. So it was not so much fine tuning of the networks. Probably we can see improvements even there. But we went on the assumption and the conclusion. If even like this, it's so good. Even working more on that, probably the results can get even better. Which shows that the chaotic systems can be easily identified, which is not so much good for cryptographic purposes.
Yeah. Okay, so let's thank our speaker again.
Thank you.
Okay, so now we have the next speaker. If you can share your screen.
Okay. So just a little bit. Okay. Can you see my screen? screen?
Yeah, perfect.
So, good afternoon to everyone. A really nice presentation so far. So I'm here to present you this work called A Comparative Study of Optimization Models for Super Ellipsoid Fitting in 3D Objects. And this was a joint work with Fernanda Costa and the master student Maria Silva. And so in here we have an illustrative picture of a robot which has in this case, one arm with 7 degrees of freedom, which is the same flexibility as a human arm. And in the super quadratic problem for fitting clouds of points in modeling 3D objects, and in here we have some objects that we used in the experiments, is a quite relevant problem in robotics and also in computer vision. And why is that?
We are not seeing the. Did you change the slide? Or are you still in the first one? Okay,
no,
so
I changed it.
Okay, can you maybe
start
share and start it again?
Maximize.
Okay, wait. So I'll do it again.
Yeah.
Window, time screen. Well, can you see it now?
Yeah.
It's changing, right? Okay, so like I was saying, modeling 3D objects from a cloud of points. It's a quite relevant problem, and in robotics, also in computer vision, but in robotics, which is the main focus here, we need compact and accurate geometry representations of all the objects in the workspace of the robot, and superquadrics, in particular super ellipsoids, offer a good balance between flexibility and simplicity. In this work, what we will present is two optimization approaches that are compared, one that considers the implicit form of surface fitting, super ellipsoids in particular, and another one which is volume-based fitting. And so just going right to the first model that we have considered, which is based on the implicit surface fitting. In this case, the objective is to minimize the distance between the cloud of points and the surface, the super ellipsoid. And as constraints, we have that all the n data points must lie inside the super ellipsoid, and also in the expression 3, that all the bounds on the parameters of the super ellipsoid should be within a lower and an upper bound. In this case, for these specific superquadrics, the super ellipsoid, we have 5 parameters. The first 3, lambda 1, 0, 1, and 2, are scale parameters along the 3 axes, x, y, and zeta. And the last 2 are shape parameters that control the roundness or squareness of the surface. The second model aims at minimizing the volume of the enclosing superquadric, and it also includes the same constraints as before. As a solver, we use a sequential least squares quadratic programming, which was developed by Kraft in the 80s. It is based on sequential quadratic programming and well suitable for nonlinear constraint optimization problems that where the objective and the constraint functions are sufficiently smooth. We made the results, the experimental results, in Python using the PySQL KP, and which is widely used. And in here, the sub problems are solved using quadratic approximations with linearized constraints. The SCN matrix is updated through quasi-Newton approximations. And just going a little bit fast on this, in each iteration, so the SQL key main steps are the computing of the gradients of the objective and constraints, also the building of the local quadratic approximations of the objective function, and the linearization of nonlinear constraints, and the subproblems with linear constraints are solved using quadratic programming and updating the solution based on the results that are obtained for the subproblems. We have chosen this method in particular, well, since it is able to handle nonlinear constraints and both equalities and inequalities, and it supports simple bound constraints. It is numerical stable and robust in convergence, and also because it's freely available in several optimization libraries, which is the case of CPy. So in here, I will present results only for free objects that were considered, that were already used in experiments with robots, where we consider a cloud of points, and in this cloud of points, we have in here, so these three objects, we can see in here a real scenario with the robot, where we had a nut, the pink, wheel, which is a green object, and a column that is yellow, and it could be yellow with another combination of colors. And so these are objects, free objects that have different characteristics. Some are more long, other are shorter. They can be circular objects with holes or without holes, and they could have some segments and not being so round. So it's interesting because of that to do the experiments with these objects. We standardize all the object dimensions, and given that we have nonlinear optimization problems, we did some preliminary tests because we were expecting that the solver could be trapped in local minima. This is why we did the preliminary tests, and so it looked like there was some dependence on the bounds that were specified for the first and for the second model that we used. This is why we consider a total of 27 combination of bounds for the parameters of the superellipsoid. For the case of the last three parameters, the ones for the squareness or roundness of the forms, we just consider bounds used also in literature of 0.1 and 1.4, while for the upper bounds, we consider for the three parameters these 60%, 70%, and 80% of the radius of X, Y, and Z. And I'm sorry, there is a little mistake in there. And so, as for the results, in here we present not the 27 cases for each object for model 1, but only the worst with the W and the best with the B in the table. And for the nut and wheel, we can see that the optimal objective function value, that in this case evaluates how close the superellipsoid surface is to the cloud of points, is around, well, is minor than 10 to the power of minus 6. And specifically for the nut, we can see that the worsened cases are very similar in terms of the objective function, 10 to the power of minus 7. And in the values of the first three parameters, we have some variability between 8 to 17. So there is something happening here. So the solution that we found perhaps are different local solutions. The differences in the three last parameters are not so big, also because of the nature of the bounds that are set. For the wheel, the results are similar also, but in here we have even a larger a larger discrepancy in the theta zero value. For the column is an object that has, okay, this larger part where we consider several points, but it also has these tips. So it is a more complex than the other objects in this sense, because you will always have some data, some cloud points, the ones that will be in this area here, that will be farther away from the surface, because we are only using one single super ellipsoid for each. And in this case, we see also that however there is points that are inside the super quadrant that we are expecting it to be because of the shape that we are using, the difference in between the worst and best case are 10 to the power of -8, so they are quite similar. This doesn't mean that it's best than the previous cases, but it's just a difference between the best and worst. And the parameters are not so dependent, or at least they seem not so dependent on the bounds that we impose, on the upper bounds, on the values of the parameters. In here, I just am presenting the worst and best cases for the nut, the wheel, and the column. They are quite similar. Well, in here we can see that for the best case, in the case of the nut, it's more round and it seems more fair when compared to the objects that we have, but well, the results could be better, at least. When we go to, well, looking at results, at least for the nut and for the wheel, it seems like there is some correlation or some association between the upper limits that we set and the values of the optimal parameters of the super quadrant that we are considering. And in fact, for the nut, we can see that we have in here in bold one correlation that is statistical significant and is negative, which means that as the limits of lambda 1 increases, the optimal solution will decrease. So as the lambda 1 upper limit increase, the lambda 1 upper limit that we impose on the constraints of the problem, we have a tighter fitting of the superquadratic to the surface, to the cloud points that is found. We can see also for the wheel that we have two significant results here, correlations, Spearman correlations. This was correlation that was used. And also there is a negative value for this. For the column, we didn't find any limit association, okay? So we will go now to the second model. And for the second model, also starting with the column, we can see that the difference between the best and the worst is more or less similar to what we found previously, 10 to the power of -7 now. In the model 1, it was 10 to the power of -8. In this case, model 2 considers that as the objective function, we have the minimization of the volume of the superquadratic that involves the object. For the nut, we have better results. Now the difference between the worst and the best case is only 10 to the powers of -10. And the lambda 0 to lambda 2 parameters are quite similar. They are the same until the 7th decimal place. And for the wheel, the objective function is also, the difference in the objective function is also 10 to the power of -7. So the worst and best case are quite similar. So there seems to be no association, and we tried this. We computed the correlations, and no significant statistical significant correlation were found. When we compare the results from model 1 and model 2, in terms of the volume, well, the volume is important because, okay, it's how much space you are considering that the object occupies in space. And this is relevant because you are you have a robotic arm and hand that will grasp the object. So it should be big enough, but smaller as possible. So the volume should be as small as possible. While model 2 minimizes explicitly the volume of the superquadric that we use, in model 1, this minimization is not explicit. So we are just trying to fit as close as possible the surface of the superquadric and the cloud of points. This somehow also implies well, not a minimization, but a decrease in the volume of the superquadric. But in here we can see, as expected, that the volume of the superellipsoid that is fit on the object is smaller when we use model 2 than when we use model 1. It was also relevant that, for example, while for the column, the best solution, the one with the best objective function, fitting the superquadric as close as possible to the data, to the points that we had, present a smaller value than the one used for the one obtained for the worst case. In the nut and wheel, well, this was the other way around. Actually, the volume is larger for the best case than for the worst case. This could be explained by the fact that these objects have a hole inside, so this makes them different from the case of the column. Also in here is the best case and the worst case for the nut, the wheel, and the column. And in here, I suppose you can see that now the results, at least for the wheel, are better than we had in the previous model. And these are the results for model 2. So in conclusions, we found that while it was expected, we were expected that there is some sensitivity on the optimal solution of the upper bounds imposed on the superquadratic parameters, but this happens not for all the objects. We here present results on 3 objects that are commonly used. We also tried others. This occurs in some objects, in this case in the wheel and nut, not for the other object. For the column, this doesn't occur. Also, the volume-based model allowed more compact and accurate representations and lower sensitivity to the upper bounds of the parameters that are set. This seems that the volume minimization that we consider on model 2 provides a more robust and feasible model of the objects that we are considering. In future work, actually it's ongoing work, we expect to extend the analysis to other superquadratic families. We have tried some, and explore more complex geometric shapes. And thank you very much for your attention. And here we just have some of the references that we have on the paper.
Thank you for the nice presentation. So we have time for some questions. No questions? Okay, so why a superquadric?
Because we can have implicit equation that defines the surface of the superquadric. And what we want to do is, okay, we have the objects and we want to find a function that represents the surface of the object. And this representation of the object is the input of the motion planner for doing the movement of the robotic arm. And we are doing this, the movement of robotic arm, the trajectory is obtained by solving nonlinear optimization problems, and we are using exact formulations that need this function of the objects. And this is why we use the superquadric, because it's possible to get that really nice function, the implicit form that will be the input to the optimization, to the trajectory optimization problem.
Okay. Any questions? Last minute questions? No? Okay, so thank you very much. Thank you to all
Thank
the
you.
audience for coming to this workshop. This workshop continues tomorrow at 9 a.m. with 2 more talks. And I hope you enjoy the wine. If you don't go to the wine, just enjoy the city.
Have a nice evening. Bye-bye.